Hi and welcome to the next session at Meeting C++ 2025. And this time it's to lie and hopefully to lie usefully. Patrice, this is such an interesting title. And I do wonder what you're gonna lie us about here now.
Well, I don't want to lie to you, my friend.
My
But
old friend Patrice from Canada joins us now in the online track. I'm so honored. Thank you for being here. Please take it away.
thank you for hosting me. So, just so everyone knows, I'm in between classes right now, doing this from one of my offices. And I don't want to lie to Jens. I want to thank Jens for hosting me. I've been wanting to go to Meeting C++ for a long time. I cannot because it just doesn't fit with my teaching schedule, but I'm glad to contribute something this time because it's a really cool event. And Jens is a very cool person. So, I have been planning to do a talk on lying for a little while. I'm hoping you will like this. It might be abstract at times, but let's see what we can do with this nonetheless. For those who have seen talks from me, I'm a member of the C++ Standards Committee. I've been there for a bit more than 10 years now. I've been teaching since 1998, college and university both. I work a lot with game programmers. And yeah, this is mostly what I do. I have lots of kids and lots of animals, but you won't see them in my office today. But you would see drawings if you were there with me, but you're not. Um, the Normally in my talks I do a lot of live coding. I like to do live coding. This one hasn't been planned like that, although there's a lot of code and it's a bit abstract. But I will give my slides to Jens, and for most of the slides you will see links to online implementations that you can actually try and play with. Should you be unconvinced, because we're talking about lies, aren't we? Because we lie. No, we all lie when we program, but hopefully even in real life, hopefully we don't lie much. You can hide gifts that you want to give your spouse or your friends and tell them, no, I don't have anything, although it's a lie. Or you can try not to tell your kids about why teeth get changed for money in some cultures at the very least when the teeth fall from children. Um, Sometimes you have lies that are not as nice, and you try to keep them to a minimum if you can, because it makes people feel bad, and that's not good. Telling the truth is a good thing. But when we code, we do lie all the time, and one of the names for these lies is a cast, for typecasts. Um, these are things we do when the compiler sees things and we don't want it to see what it sees, really. We want to give it another perspective on our code. We purposefully lie to the compiler for many reasons, as we will see. So this talk is about casts, really. How you cast to lie to the compiler to make it do the things you want it to do. And sometimes to get yourself into trouble if you're not careful enough, of course. Um, yeah, sometimes we're not lying. Sometimes we're just telling things to the compiler that the compiler might know but doesn't, about the shape and form of the data. Maybe the fact that we know that our data will come in blocks of some size, or that we know that the bit patterns they're actually an object that the compiler hasn't seen being created yet, but it's an object we know, we built it purposefully. So it happens sometimes, but sometimes we're just lying, of course. So the less lies, the better, but we have to be practical. Um, so we look at the various casts in C++, including the C cast. It's not going to be a core-ish kind of talk. I'm going to be informal as much as I can, otherwise it gets very dry very fast. But I left links to the actual sections of the language that describe the cast if you want to look more into detail in a more rigorous way about what we're talking about. And towards the end of the talk, we'll try to look back at things and see why do we lie really? Okay. This is the kind of code that you could see in your code, and it might warn, because you're kind of losing information, maybe because you're storing a double and a float, so it's not two floating points of the same size. One is more precise, your literal is more precise right now than the object you will store it in. So you might get a warning depending on the compiler. In some languages, this won't compile. In C#, for example, this requires a cast. Uh, you can cast like this too, saying, well, it's a double, but I'm telling you it's a float, and I'm telling you this in such a way that you can take that into account at compile time, so the cast is fine for that. Or you could just tell the truth, of course, which is even clearer. So these three actions will probably lead to the same results. The first one might warn, It's probably a very little white lie because we do that all the time. And the other two are other ways of expressing the same idea. The middle one is a lie. We're just lying. But maybe it's fine. Maybe we don't like the F suffix. Um, this is also a case where we have a lie there. We have a base and derived class. The derived class is a public, the so a public derived class from B. So you have a D object derived. Well, you can't cast it to its base class with a static cast. It's a reference to the same object. That's fine. This guess is made for that. And you can even, in a case such as this, don't lie. Both work. So in this case, you might be saying, well, maybe the static cast, even though it has no effect really, because not writing it does the same thing, maybe it just makes my intent clearer. So sometimes you just lie to make people understand what your plan is. In a case such as this, though, it's a bit different. Because if you try to think about this code for a little bit, you have B, a base class, and you have two derived classes, D0, D1, and something that derives from both D0 and D1. And then you go from D to some B. But look at the second line in main, the line where my mouse is moving right now. This wouldn't compile because the question is, which B? This is the shape that you have. There's two B's in a D. So if you try to cast a D to a B, well, you get an error saying, what the hell are you talking about? There's two of them. Which one do you want? They're not even at the same location in memory. Well, in a given D object, they both occupy different storage spaces, at least if you put some data members in there at some point. But if you do cast either to D0 or D1, then you can implicitly cast to B, and that's going to work fine, although you're going to get different Bs in both cases. So sometimes a little cast like that lets you nudge the compiler towards one of the paths that are possible to you and lets you remove ambiguities from your code. This is fine. It actually happens in real code. So the students that I have, especially in college, and even undergrads, sometimes they confuse casts. They think we are mutating stuff. They think we are changing the nature of the object we are casting from, but that's not what it does, really. No, it changes the perspective on an expression. So the expression's result stays the same in practice, but the look we have, the look we take on that thing is a bit different. We're saying, it's a D, of course, but I want to look at it from another angle, as if it's a D0, and I want to make sure it's fine, makes sense to me. Sometimes it just changes the address a little bit because the objects are in the same location in memory. So it's just a little lie. It doesn't change the nature of the thing. Okay. So yeah, this one would be ambiguous, as I said, although these two work, but they would lead you to a different B in both cases. If you compare the addresses of the Bs there, they might not be the same, depending on the optimizations that you make. It's kind of like doing this, if you think about it. It's like taking an additional step to go one way up in the class hierarchy, either on the D0 side or the D1 side, and doing it step by step. But the cast lets you maybe make it in a more direct manner, I guess. But you're saying the same thing, really. Cool. Now, there's many reasons to lie. And depending on the lies you do, the lies you make, you will get different effects. So there are different reasons for having different casts. So that's why we're going to take a look at them, because there's quite a few in C++. There's the traditional ones like this. Traditional, I should have put quotes around this because they're traditional in C++. But they look unusual to people coming from other languages, including C sometimes. They are the ones that you see there. So the static cast that we'll spend most of our time on because it's probably your go-to cast. It's like the vector of casts in a sense, is the one you use the most. Dynamic cast, which is a different beast altogether. Const cast, which scares people, but actually plays an actual cool role in the system. Reinterpret cast, which is a peculiar way of saying, no, that thing you're looking at is not what you think it is. And then the ccast and its counterpart, the function stylecast, that don't exactly do the same thing, but are kind of grouped together. With the recommendation to steer away from them if you can sometimes, in very specific reasons, because they're not as clear about the intent as the others are. Let's start with this. As I told you earlier, I tried to leave links to the actual sections on the online version of the standard that we have. So you cannot take the whole standard with this, but you can bits and parts of it, and they're always up to date. So it's pretty cool. So because I'm being informal, so if you need the formal stuff, you can look at it. So for most programmers, especially if you look for performance, this might be your best one. It's context friendly. It's usually doable at compile time. It often costs you nothing, and if it costs you something, it's probably the thing to do still. Okay, so this is the most important one, I guess, for most people. It's probably the one we look at the most. Um, so if you need to cast between fundamental types, so int float, long int, or something like that, this is probably like the right thing to do. I mean, they would maybe work with other casts if they're not lossy. If you're narrowing, if you're losing some information, like moving from a big long to a smaller int or something like that, you might get a warning depending on compilers and warning levels. So casts may be your way of saying, "I know, please shut up, please let me do my thing. I know what I'm doing." Um, so something like this. You might get a warning on N0. Okay, you might, because if you think about it, you're losing decimals there. Okay, so it's considered to be a narrowing thing. Some compilers warn, some compilers will not. The link I put there doesn't warn on this. It depends on the compiler and setting. Um, something like this shouldn't warn at all because you're casting a double to an int. Now there's a cast. So you said I want it. So it's a deliberate gesture on my part. So if you get a warning there, it would be very surprising because you took responsibility for the gesture. You lied explicitly. Doing something like this, well, whether you write N0 or N1 to X, you'll get pretty much the same thing in this case. It's going to work. And it's not considered lossy, although one could debate on this, because if you get value 3, store it into a double, well, depending on the actual value that you have in your integer, it might not be exactly representable in the floating point value that you have, because precision matters in these cases. But it's not considered warning with respect to the language, so you shouldn't get a warning with this one. So Sadicast can remove a warning in a case like this, or potential warning, by clarifying the intent. I took this noisy thing, which is not from me. It's from I took mine at least from Mr. Lavavai at Microsoft. It's a nice trick to try to learn how move semantics and other things like that work. I didn't put the whole class there, but you have the whole class in the one box link above. So it's something to track what's going on in your code if you're copying things, moving things about. The noisy in its lifetime tells you what's going on. Am I being moved? Am I being copied? So I have two f functions there. One that takes a noisy by ref, and one that takes a noisy by r value ref. The kind of thing that you get from a dying object and anonymous object, or something that has been moved from. So if you look at the calls in main below, there, the first one takes an L value, N0. It will call f of noisy ref. If you call f of static cast of noisy ref N0, you won't get a move in this case, but you will get a call to f noisy ref. You're not moving from something, you're just changing the perspective locally on the object. And if you pass an anonymous object like noisy brace in this case, an empty one, default noisy rather, since it's unnamed, is going to call the noisy ref version of f2. Now, take a look at the two f functions in the middle that you see here. I'm just going to slightly change the signature there. I'm going to pass them by value instead. So if I do f of n0, I'm doing a copy, and this is what will be printed out. If I'm casting to a dying object or calling stdmove on n0, it's going to call f of noisy. Again, there's only one, but to create a temporary, it will use a move constructor. So in both cases, whether you do move, which will cast to noisy ref, or just do the cast yourself, you're going to end up with the same results. You should probably use stdmove in this case to make your intent clear. Again, move is a kind of cast if you think about it. Fine, my friends? So this is a more complex one. So it looks like spaghetti in a sense. So you have a base and two derived, publicly derived objects or types from B. The main is the tricky thing there. Okay, so you have one D0. So you have two possible derived classes, D0 and D1. There's one D0 there. Taking a reference to a B from D0 is solely fine. You could static cast, but you don't need to because it's your base class. So it's fine. It's a public base class. Downcasting, the commented out thing. Okay, this one is dangerous because you could be making a mistake. you could be going to the wrong derived class. But in this case, I'm doing the right thing. I'm casting back. I'm trying to take a reference to the original object of the same type. But downcasting without a cast is considered to be a dangerous thing in C++ for good reasons. Because if you make a mistake, you might be in trouble. This one will work. It's a downcast, and you're asking for it. You're saying, well, okay, well, I want to take a base ref and cast it to the derived base, and I know what I'm doing. If you know what you're doing, do it. It's going to be an essentially no-cost thing. You might pay for a little offset in memory, and that's it. Of course, if you're doing the wrong cast, you're casting to the wrong derived class, well, it's a cast. So you said, I'm taking responsibility. I know what I'm doing. And of course, you don't know what you're doing in this case. And you're getting everything wrong. Well, this compounds. It's a lie. You have to accept the consequences of your lie. So doing downcasts with this cast is fine as long as you know what you're doing, because it's the almost free way of doing it. But if you make a mistake, dangerous things will happen. So if you ask me which ones, I don't know. You're in undefined behavior land. I don't know what you're going to get. Fine. So I'm not saying do this. Don't. Unless you have a controlled situation where you know what you're doing. This one is interesting also. I know it's all abstract stuff, but think about it. I have a base class B, and I have two derived class, D0, which is publicly B, and D1, which is privately B. So that means, if you're not familiar with private inheritance, I know that it's a concept that some languages don't have. It means that D1 knows it's a B, its friends know it's a B, but derived classes from D1 or other parts of your program don't know about that relationship and cannot benefit from it directly. Okay. So in this case, in the main function, casting a D1 to a B star, it's not possible because main doesn't know that D1 is a B. It's not aware of that. This is private inheritance. If you call F, which is a friend of D1, well, because F is a friend, F knows about that relationship, and F can cast to a B star in this case, with a static cast, essentially a no-cost thing again. So static cast will respect the rules. If you do not have access to the kind of type relationship you're trying to express, it won't work. It's a nice cast in that way. There are other casts that are less nice than that. So static cast is cool for this. It respects the rules. And if you have a friend, or if it's yourself, well, you know about the relationship, and you can use that knowledge to good effect. Cool. So if you're trying to cast to void star or from void star, that's an interesting case. You can kind of see there are languages where there's an object-based class and everyone is an object in some sense, and there's a lot of virtual member functions, so everyone is polymorphic all the time. C++ is not like that, of course. But from a perspective, you could claim, even though this is very informally speaking, that all pointers are addresses, which is, I'm really cutting corners here because the situation is much more complex than that. But from a programmer's perspective, that's often enough to write day-to-day code. So an int star, it's an address. So, and a float star is an address too. And a string star is an address. They're all pointers. So you could conceptually say that their base class, lots of quotes there, is void star. They're all addresses. For that reason, you can cast to and from void star to something else with a static cast. Of course, you have to be careful because casting to void star, it's implicitly correct. Casting from void star, you're just removing the protection of the type system. The type system has to accept your claim that the cast is correct, but you're writing it in your code. You're saying, I think this is the thing to do. It's a lie that I'm making. I'm telling you, compiler, you don't believe me, you wouldn't do it without my consent, but I'm giving you my consent, do it. Now, you have to have the same constant volatile qualifiers. So you can cast from a const int star to a const void star, but you cannot remove the const along the way. Cool. So code like this happens in operating system interfaces sometimes. So I have this kind of operating system thing type, and I have an OS call, takes a void star in my code. This is something that actually happens in real life. Lots of functions look like that in your operating system's API. Um, so you might have an object that's an operating system thingy. Well, you can pass its address to that function. It takes a void star. So you hope that's a proper thing, but you probably read the documentation before calling the function, I hope at least. You can also set a cast to void star. Fine. You can also take the address of thing and put it in a void star. That's also fine. It's an address. Oh, that's what you're saying. It's an address. But through the void star, you're losing type information. It's type erasure with pointers. I mean, this is commonplace, but you have to be aware that you just lost protection. And if you want to cast back from void star to your operating system thingy star, you're going to need a cast, at least in C++. I think C is more lenient than C++ for this. But if you do a static cast, it's going to work. It's going to work essentially freely. And you're going to get the same object that you used to have. This is kind of guaranteed. But because it's the same address. You know? But if you make a mistake, you're on your own. Yeah. It's totally safe as long as you know what you're doing. Reinterpret cast would work for that too. Reinterpret cast, though, is we'll get back to that. We'll get to that a bit later on. It's a more edgy thing. You can make more mistakes, and it's less const_expr friendly than static cast. Static cast tends to work well with const_expr code. So if you have the choice between the two, you probably want static cast to make sure you do the right thing. Okay. So probably it's better for most use cases. There are reinterpret cast use cases, of course. So this is a potential C++26 code. So as you can see, as I have this const_expr int object in my main program, and I'm asserting that if I call compile time maybe with the address of n, I'm going to get 3. Now, if you look at what that function does, it takes const void star, which is fine. I'm taking const int star, so it's implicitly convertible to const void star. And within the function, I'm casting it back to a constant star. This is actually correct C++26 code. It compiles and it works. Surprisingly, maybe in some sense, because it's tricky. As long as you don't do undefined behavior stuff in there, you're going to be okay. It's the only cast that will get you there, though. Cool. This is an example that doesn't compile, just to make sure it doesn't compile. It almost does, though. It almost does, because parts of it will compile, parts of it will not. You might notice that I'm not using static cast in my function right now. It's deliberate. Okay, so this is incorrect code. You will see a link that doesn't compile if you play with it. So far, at this point, when I'm playing with derived to base, references, and reinterpret cast of b to an int ref, because if you think about it, the int is at the beginning of b. So I'm kind of saying, well, that thing there at that very precise location, it's an int, believe me. So I'm trying to do something a bit dirty there for some reason. The compiler will actually let you do that at compile time. It's going to work. Okay. When you try to do the interpret cast to void star, though, it will let you at runtime do this, but it won't let you do this at compile time. This will not pass. It's asking too much from your old compiler in that case. If you do this with static cast, though, it's going to work. It's going to compare the addresses of B and N, and indeed they are the same in this case, because layout-wise, you're looking at the exact same location. N is exactly at the beginning of B. There's no virtual member functions. It's going to compile, it's going to return true. Okay, so static cast is your tool of choice there. Even though this is very dirty code, it's not invoking undefined behavior in any way, and it's actually going to work. All right? So one thing that's cool about those const_expr contexts, which is another reason to prefer static cast, is that they do not allow us to do undefined behavior. Your compiler is supposed to diagnose an UV in const_expr contexts. So if you're going to cast stuff in a const_expr function, you might be able to remove some UV from your code. So static cast is the good way to lie in such a context. Now, my examples, you will see, I could probably do them without static casts, but just to show it works. Okay. So looking at this one, if you don't mind, we have two derived classes from B. One is a float, one is an int. They're at the same relative location within the D0 and D1 objects, but here. So if I'm converting from D0 to B, which is its direct base class and it's a public inheritance, no cast required. Casting B to D1 is incorrect, of course, because B is not a D1. It's referring to D0 in this case. And trying to get that N thing in there, it would be dangerous. So we'd be getting the int, but an int is a float. It's UB. So the static cast would normally work. It would work in another context and get me in trouble because I'm doing the wrong thing. But in this case, it's not going to compile because it's UB. It's going to be diagnosed by your compiler. It's kind of neat. So if you're doing some kinds of weird maneuvers, sometimes you want to make sure you're doing something sane. Just try to get the compile time. Sometimes it informs you that you're just doing the wrong thing. This one too. It's a very simple function. It takes the maximum value of an int and tries to return the fact that n plus 1 is greater than n. But this is signed integer overflow. So even though this would give undefined behavior at runtime, at compile time, it will not compile. The context per context, this thing doesn't compile because you're invoking undefined behavior in the context per function. So again, if you wanted to lie, the static cast to bool is not necessary in this case. If you want to lie, well, lie with static cast. That way you can check for UB along the way. This one is also an ST one. So I'm using a union. So in a union, the N and the F are the same address in memory. And I could have static asserted on that, but they probably have the same size and the same alignment. I'm initializing U.N in this case to 3 because it's the first member of the union. That's how it works. And I'm casting U.F to an int. Probably would make some kind of sense in some context. Some people believe it works, but it's actually undefined behavior, that thing. So you're reading from a non-active union member, it's not going to work. There are situations where you can do something like this. It involves something called the common initial sequence. There's none in this case because floats and int don't share that common initial sequence. It would maybe work with an array of 4 bytes. So this thing... This thing will not compile with the cast in this case because I'm doing something incorrect. Without the cast, it doesn't compile either. It's still undefined behavior. But if I'm trying to do a cast, this is the cast I can try to do in a context per context that will maybe reveal stuff. Cool. You cannot use static cast to cast away const. You nasty person if you're trying to do this. Adding const is fine. You're not losing anything. It's pretty cool. But and adding volatile too. But volatile is a more niche kind of thing. It's less well defined than the standard that const is. Const is very clear. Volatile, there's lots of interpretation about what it really means. So it's less common than const. But both would work. So if you want to cast away const, your cast is const cast, not static cast. So trying to do something like this. Gaining const, Cn, that's a reference to n. It's like taking a const perspective on a non-const object, saying through Cn I won't be modifying the object, through n I could. If you're trying to do the reverse, trying to take a reference to a non-const thing from a const reference, no, that won't fly. So the thing that's in comment right now, you're trying to cast away const, and this is not the right tool for you. It's a good thing. No, it's not a magic wand. It's a targeted way to lie for specific tasks. And this is not the right task for static cast. It's cool to have the names for this thing. So if you're looking for something that casts away const, you know that you're not looking for that. This is another weird way to use static cast. Sometimes if you want to add const, because if you want to add or remove const, in general, you have const cast for that. But adding const, static cast works. Look at main. So you're below. I have a non-const x there. If I'm calling f, well, there's two f's, one that's const and one that's not const. The bad idea is having two functions that are essentially the same, but do different things, and one of them is different from the other just based on the const qualification. This is a horrible API design. But so the fact that you can do it is troublesome as it is. So you might be wanting to call the one that returns 4, but with x.f, you're going to call the one that returns 3 in this case because x is a non-const object. So it's going to call the non-const f member function. When I'm doing f of x, I could be doing f of x with static cast, with const cast, or I could just leave the compiler to do its job because gaining const is not a dangerous operation. Well, within the context of f there, x is a const object. So doing this, if you call x of f, you're going to call the version of f that returns 4, not 3, because it's a const version. You cannot downcast to call f from within the f function to try to call the other one. If you want to do that, it's a const cast. Static cast will not give you that. Okay. So you might be wondering, so it works for upcasts, it works for gaining const, it works for the safe stuff. It also works for downcast, but if I make a mistake, I'm gonna really get in trouble. It's a dangerous thing to do. So why am I allowed to do that? Well, sometimes you know what you're doing. Sometimes you, by design, have constructed something where a static cast is totally safe because you know how you build things. So I stole an example from sections of the standard library tied to the IO streams mechanisms. It's not really an IO streams thing. It's more a customization of the way we do some IO on some specific types. Um, it's called facets. Okay, so I'm just going to give you a quick overview so that you get the ID of this thing and why static cast is a cool thing. So you have this base class there. Okay, I tried to highlight the important stuff. A facet is something that has essentially no data member, no member function, except for a virtual destructor. So the common aspect of all facets is that they are virtual destructible. Okay, let's put it this way. And it's normally seen as a bad thing to have a virtual destructor when you do not have any other virtual member function, but in this case, it's by design. Okay, we'll see why later. Internally to that, but it's public, there's this ID class. So facet canonical ID is a type, and that type is a very simple thing where each object of the type has a different val object. This is not thread safe, but it's normally used at startup in a machine anyway, so nobody really cares. And it can be compared with operator less than because it's often used in a map as a key. So yeah, that's it. So each facet ID is a different number. And what we're building here with facets is a type numbering system. Well, right now there's no static cast involved. It's just the basis of our skeleton. Okay. My facet wrapper of F there. F is any class I want to use as a facet of sorts. Okay. I did this in a non-intrusive way, so I can do a facet wrapper of any type that I feel like. Facet wrapper is a facet. It's a public thing. It owns an F object inside, so the F is stored within, and it has and that's the important part, an ID static data member of type facet ID. So each facet wrapper of F has its own, we're talking about the type here, has its own ID static data member, and each of them has a, by design, different number. We're building a type numbering system. So for some type F, this wrapper of F canonical ID is a very specific number. It depends on the order in which we construct the facets in a program, but within an execution, it's always the same. Cool. Now, my server, I'm going to put facets somewhere so that I can retrieve them later. That's the goal of this thing. I'm going to put unrelated objects together through the system. My map associates IDs with pointers to facets. With facet, remember, it's a base class that has no other function than the virtual destructor. So the fact that we're using unique pointers there is to automate the destruction of the facets at the end of the program. That's it. So I'm doing a mapping from an ID to some base class somewhere, but I'm not going to be using facet with virtual member functions directly apart from the destructor. I don't know what the actual facets do. I don't want any relationship a priori in there. Okay, it's a singleton for the purpose of the example. When I install something, well, I'm making a wrapper of F, and I'm trying to find if it's already been installed because I want one facet per type of facet within the system. If I have one for sound, I'm going to replace with a new one. If I have a new one that comes up, there's not going to be two, it's going to be a single one. So I'm finding it. And if I find it, I swap the value but keep the key. It's always the same ID for a given type. The value might change. Otherwise, I just install it. Remember that it's a map of unique pointers, so it takes ownership. And then the trick, and this is where the static cast comes in, is the facet function below. So someone wants to get a facet from a type, so facet from a sound or for textures or for whatever. It calls the facet member function where I look for the ID of this wrapper of F in the map. If I don't find it, it hasn't been installed. But if I do, even though I have a pointer to a base, I'm convinced that it's a pointer to a facet wrapper of F. So I know that it's F and nothing else. And I can set a cast to that. The only way to get there, really, unless you did some Machiavellian cheating, is to have installed the thing in the first place in the proper way. So I can give you, with a lookup, a pointer to any unrelated object that has been stored inside that thing, and you can use that object afterwards without any indirection because you get a direct relation, well, a reference to the actual object. There's no virtual member functions to call or anything. It's actually pretty cool. And this is just a facility to use people, to help people use it. So the point is you can think about a system where you have many managers of many different things that don't have common interfaces, but you do want to store them in a proper place to facilitate lookup for these things afterwards. So a manager, something like that, maybe. So with this design, you pay for a lookup. You have a map, you're going to get logarithmic lookup or something similar. And you pay it once, though. And once you got the thing, you use the object, but not through an interface, use it directly. So I have a texture manager that produces textures, very simple stuff. As you can see in this code, there's no base class imposed, there's no virtual memory functions to implement, all very easy. Of course, it's extremely simplified. Same thing for sounds. I have a sound manager that gives me sounds. There's no relationship between the names of the member functions or anything. But when I install a texture manager or sound manager, at a later point, I can get them, use facet does a lookup. And once I have that, I could keep a reference to it or just use it right away. And then I can call non-virtual member functions of unrelated types. But set cast is the key that makes this efficient. I can downcast from the facet base that is completely unaware of the derived classes that I have built for them and get them directly and efficiently afterwards. So it's a very cute design. You could probably do the same thing more efficiently with variant today, but you would be less extensible. So it's a matter of trade-offs. If you want more extensibility, this is cool. If you want more speed, variant is probably a bit faster there. So see, downcasts sometimes in a controlled setting, they're really fine. So we get there. Some people are fans of dynamic cast. I must admit I'm not, but I do understand that we have to be practical sometimes. Okay, so when you're getting a dynamic cast there, is because you want to be able to validate that the cast you're trying to do is actually correct. So you want something that you can check. Normally, it's to allow you to do safe navigation through a class graph. Okay, so it's important that your source type from the cast is polymorphic because we, in practice, store the information required to do that sometime somewhere in the VTBL. Okay, whatever it is. If you do an unambiguous upcast, like the F function there, that casts from derived to base, dynamic cast will work even in non-polymorphic settings. I must admit that I didn't know that. I learned that writing the slides. But the downcast requires polymorphic type because the information is there. All right? So if you want to do a downcast, it needs to be checkable. And for that, well, you need some metadata inside your code. This depends on RTTI, so runtime type information. So if you use this thing, you might have slightly bigger binaries than if you don't. But if you already have RTTI, it's not costing you more to use that. Now you have D0 and D, 2 layers. Same principle. If you're doing an upcast from D to B, even though there's an intermediate step, it's going to work fine without virtual memory functions. If you're doing a downcast, the source has to be polymorphic again. Okay. This is more realistic though. So you have B and D, and you have a polymorphic B. Okay. So the F function that goes from derived to base, I do a dynamic cast. I don't really need it, but I do. Okay. The downcast in G, I need a dynamic cast to do that because it might be okay, it might be incorrect. It depends on the other derived classes that exist. And it requires B to be polymorphic in this case. As I said, the source type is to be a polymorphic type. That needs to have at least one virtual member function, which I do. So the cast in the main function there lets you check that dynamic cast will work or will not work depending on the cases. It should all work in this situation because it's all clean, but at least you can check them. So if you cast between pointers with dynamic cast and you fail, you're gonna get a null pointer. If you cast with references, you're gonna get an exception. Depends what you're trying to do. This is a situation where there's two different base classes, B0, B1, with another layer D0, D1, and at the end, D. Now look at F there. F is tricky a bit. F is taking D0, so we're on the middle left side. There we are. And we're trying to guess it to B1, which is on the upper right side. Now that might make sense if we're having a D object that is both a B1 and a D0, but to get that, you need to navigate down and then come up. It's not a trivial thing to do. Static cast won't give you that. Okay, for this kind of navigation, it's dynamic cast that you want. But if you have a design like this one, you probably have a virtual member function somewhere anyway, So this is the case that you have. If you want to do something like this, go to one of your siblings on the other side or do complex class graph navigation, yeah, this is a proper cast for you. Fine? Cool. Of course, in languages that don't even have that concept, it's not much of a bother. So normally, when you're doing something like this, it's probably a sign that something's wrong in your code. Because really, look back at this. Why would someone cast a D0 to a B1, which could be wrong, it could be right, but how come we end up doing that in F? Why would we pass a D0 if we wanted to have a B1 in the first place? Something in the signatures of our function is wrong. But it does exist. I've seen lots of people use game objects in code and downcasting all the time and have their own version of the cast to do that, maybe because they don't want to pay for RTTI, but it does exist. Okay, but the cool thing though is that since you can grep for this, if you do have a design flaw that you recognize and you're patching with dynamic cast to ship code because you have to ship code, at least you can grep for that or do a lookup at some later point when you have some time and say, okay, how did we get there? And what would be the reasoned approach to maybe redesign the interface not to get there, something like that. Sometimes it's possible. One good thing though is that we are with dynamic casts context friendly today, at least more than we used to. It's probably more useful in generic code than other stuff, but still this kind of code works now. You have a context per base with a virtual context per destructor, which means you can construct a base object in a context per function and do it at compile time. You have context per member functions F in D0 and D1. With context per, it's not like const_eval. You can have a base class that is non-context per F and derived classes that have context per Fs, and you can alternate. The point is, if you use a context per function, if you use that thing in a context per context, the functions that you're calling have to be context per. So if you look at compute in the middle, I have two objects, D0, D1. Each has its own F. I have an array of pointers to base, which I initialize with pointers to the one in D0, the one in D1. That's fine too. This is all cool, And then I'm calling dynamic cast on both of these things, hoping to cast them to D0. For D0, it's going to work. For D1, it's not going to work, And I'm calling these F functions, and of course, the one from D0 will work. I'm going to get 3. The other one will not work. I'm going to get a null pointer. That code compiles. It's totally fine today. It's been fine since C++20 only. It used not to work. Cool. Now, if you're saying, why would I do that? I don't know. People are strange, but there might be good reasons to do that, absolutely. It's kind of building some kind of lookup table or function pointer table at compile time with things that could be used at runtime too. Why not? Now we get to constcast. So this thing scares people, sometimes for good reasons, sometimes not. But this is the one you use to play with security. You can add or remove the const or volatile keywords. You can cast away const, and that's a bit scary because it can lead you to undefined behavior, My friends, when I wrote this yesterday, I was scared. And you know what? For this program on the compiler where I tried it, it printed 3. I left the link. But the results are not guaranteed because you're playing with fire. This is UB, so what are you going to get in practice? I don't know. It depends. Yeah. So this is not the proper usage of constcast, of course. If you're doing this, you're just looking for trouble. So, but there are valid reasons to cast away const. One of these is you're using somebody else's code, and they're not writing const correct code. Maybe they just don't know. Maybe they come from a language that doesn't have that concept. So you have that log message thing there. You know how it's designed. You read the documentation. You know that the string being passed won't be mutated. People have asked for a string ref. They should have asked for a const string ref, but that's what you get. You paid for that thing. It does good things for you. And that API is, well, it should be changed to a const string ref at some point or a string view, but right now that's not what you have. So you're calling use s with use then log. Use then log takes a const string ref, so you call use f use of s, it takes a const string ref. If you're trying to log message of s, it won't work. You cannot cast away const just by passing a const thing to a function that accepts a non-const ref, because that would defeat the purpose. You can make it temporary and then use that as a modifiable thing, but then that costs you a temporary, so that's not nice. Or you can just, if you're convinced that log message won't do anything nasty to your string, you can cast away const with this. But we do that in practice because not all APIs are made equal, and some of them deserve more love or have been made by people who are unfamiliar with C++ idioms like const, usage of const correctness, and everything. So as long as log message doesn't mutate your S, you're going to be okay. You can do something else than casting away const with this. You can add or remove both const and volatile. So you can like cast from a volatile tref to a const tref. You use the references normally because otherwise you're just making temporaries. So if you do temporaries, you don't really need a const cast in many cases. So what the kind of lie you can do with const cast is lie about security qualifiers. Code like this. So I have 2 process functions. One that takes a const tref, one that takes a tref. I have a vector that is non-const. So I'm calling process of v. I'm going to call process of tref. If for some reason I prefer the const tref version, I can constcast to add const. That works too. Fine. So you can add and remove const and volatile if you feel like it. Both there's a function called asConst that can make this a bit easier on the eyes too. You can look it up in the standard. There has been an article of many years back, I think it was Andrei Alexandrescu from memory, but I'm not sure, who suggested that we might be tempted to use the volatile qualifier on member functions to mark these functions as usable in multi-threading code. So the intent is that if you have a volatile member function, you're telling the compiler to only call that on a volatile object, and you're qualifying your objects as volatile if you're using them in multi-threaded stuff. So that way, the type system helps you along. Even though volatile is not very well defined, the rules for const and for volatile are pretty much the same with respect to function calling. If you have a volatile object, you can only call volatile qualified member functions on it, like const. So you could see volatile as meaning it's used in a dangerous setting, so it has been written to be thread safe. Why not? So sometimes there are companies that write their own wrappers for operating system code because, well, maybe they can't use the standard API because there are some missing pieces. A common example is that there's no way in C++ to specify the size of the stack for your threads when you create a thread today. There's been a proposal to change that by Corentin Jabot. It's a nice idea, but it's going through a constructor, so it might throw if it doesn't work, and it's going to still not be exactly what people need sometimes. So someone wrote some people wrote their own mutex class there. So it's some simple things. We don't want to see the implementation. It's hidden behind the IMPL type there that we don't see the details of. We do have a pointer to it though. So we have an uncopyable object there because we have a unique pointer in it. And the IMPL class, mutex content IMPL, probably maps to a few texts on Linux or a critical section on Windows, or maybe a handle to a mutex if you want to do cross-process stuff. So the important thing is that the lock and unlock member functions are marked constant volatile. So the person that wrote this wanted to tell us you can use my mutex in a volatile context. So if you have a volatile mutex, you can still call that function because it's telling you I'm safe to use. And const means it won't change state if you call it. So you might be debating whether that's a good idea or not. Some people will say mark it mutable instead, blah blah blah. But it's one way to do this. If you think about it, if you have a pointer to some resource, well, you probably won't mutate the pointer. You might be changing the pointee, but not the pointer. So just to make sure that everyone understands, using volatile that way is something that not everyone agrees with. I'm just showing that for the language mechanics it will work. It actually does in practice. So you can have your own lock guard there that takes a const volatile reference to some mutex m and calls lock at constructor time and unlock at destructor time. Of course, there's more to lock guard than this, but that could be a way. So you could be requiring lock and unlock to be callable from a const and volatile object. So in our case, for the mutex class, it's going to work because they have been so qualified. And if you have your channel, it's kind of very simple concurrent queue. You could have two versions of a add and an extract member function. One that is not thread safe, but is fast. You're just adding stuff to your intermediate data or extracting from it. And one that is, well, not as fast, but thread safe. The volatile qualified member functions. So in this case, you lock guard on your mutex. So M is volatile. It's a volatile mutex. You can call the const volatile lock member function in the lock guard and the unlock also. And then once you have locked the thing and you're synchronized in a sense, you can delegate to the fast version because it does the same thing as you would do anyway. So you constcast to remove the volatile qualifier from this. That's a totally fine way to use constcast. It's totally safe too. Okay, but again, this is a contested usage. I'm just showing that it works. Cool. You are a chicken there. It's what I tell my students when I explain to them what an interpret cast is. I point someone and say, "You're a chicken," because this is really what you're saying. You're telling the compiler, it's not what you think it is. So sometimes you need to cast between unrelated stuff. An int and a properly sized array of bytes, a pointer to an int, to a pointer to a float, casting between car star, signed car, and unsigned car, all three are different types. Things that are unrelated but have some common bit in between. So then it might make local sense. It's probably non-portable. For example, if you cast an int to an array of bytes, well, what order will the bytes will be in? It depends on the platform. So something like this, I put values in an int, and then I'm iterating through the bytes. Reinterpret cast is a perfect lie there. I'm saying, well, this is probably UB, by the way. It just works. So the output isn't guaranteed. It can be from left to right, from right to left, depends on the platform. Just checking the bytes one by one. We don't have the right words in the standard to make this legal as of today, as far as I know. But it works in practice because people do that. We're just in undefined behavior land doing this. So what can you do to reinterpret cast really? It's the dirty one. So it has a long name. It's not meant to be appealing. It's meant to be, well, sometimes it's just the tool that you need. So you can convert from a null pointer to some integer. There are integer types that are better than others for that, like uint pointer t or something like this. They're not guaranteed to be on all platforms, so be careful. Convert from an integer or an enum to a pointer, so the other side. Convert between function pointer types. This is looking for trouble, but it would work. And converting between object pointer types, so pointer types within objects. It's like doing a cast to void and then casting back to something else. And converting between pointer to members. You cannot cast away const with this. So this is still not the tool to remove const. If you want to play with the security, use constcast. So this is an example that's a bit scary. You have three types. So look at A, B, and C. A and B both start with an int, but they're not around the same size. And C has a float somewhere in there, okay, at the same location relative to the others. And this print bit functions would print the bits, really the bits of some T object. And we require an integral in this case because I'm using a bit set. It just works. So looking at this beast, no? So A as an int of value 3. If I take the address of A and cast it to B, so to B star, and I look at M, looking back, M is in B, M would be 4, but now I'm pointing to the A thing, which is 3. And I assert the value, it's probably going to give me 3, even though I'm really lying. The interpret cast there is something very dirty, but I'm trying to take into account the fact that both start with int, Reinterpret cast from an int ref to a float ref might work, might not work. It's bad code. But if you do that, maybe your compiler would be lenient. I don't know. And if you try to do something like casting from a star to a C star, so pointers to unrelated types, then use F. Well, F maps probably to the place where an int is in practice. You're reading F. What are you going to get? It's UB. I don't know. But if you're printing the bits, you're probably going to see the right bits through a B star, not through a C star. And now the important part in this one is that these plus 2. You're casting to a C star and then casting back to a B star. This will probably give you the proper object in practice because reinterpret cast is said to, if you do a back and forth between pointers, you're going to get the original object as long as you respect size and alignment, at least. So, it's dirty. If you want to use this dirty thing cleanly, there are tools for you. Okay, they have been there since C++20. You can look at them a bit. You have is layout compatible. That tells you if 2 types have compatible layouts. It would kind of fit with some of the types we've used earlier today. If one, there are many rules. You can read them when you have a minute. There's this is pointer interconvertible base of. So if 2 pointers are interchangeable through interpret cast because some rules have been met. If a pointer member is at the same location at the beginning of the class, or if between classes T0 and T1, members M0 and M1 are relatively at the same place one another with respect to their respective type. So you can use these to at least validate at compile time that your use of reinterpret cast kind of makes sense. Be careful though if you're playing with this. The code that you have here mostly compiles, but if you look at the Godbold link that I left, some of the traits have not been implemented in most compilers yet. But it's a 20 thing, and we're in almost 26, so just so you know. It's always essentially free. So you're just changing your lenses. You're saying that address, really, it's not the address of an int, it's the address of a chicken, as I said. So it's tempting since it's at no cost, but setcast sometimes give you a little cost because it needs to do an offset within the class layout to give you the proper pointer you're asking for. You can be tempted to say I'm going to use reinterpret cast and save a little offset, but no, if staticast does an adjustment, it's because it needs to be done. Okay, and this example really shows you the problem. So you have B0 and B1 with both have an integer, and D that has B0 and B1 inside too. So at the beginning of D, there's the N, and then there's the M, if you look at the layout in this case. So if you cast the D star to avoid star in main there, you get a pointer to D. You can make sure that D.M, D.N are different, because of course they are. And if you do these first 2 there, you do static casts. Well, P is at the same location as what you would get if you cast a D star to a B0 star. But if you cast it to a B1 star, it's not the same location. B1 is not at the beginning of D because it's offset. It's the second class in the base classes. If you do reinterpret casts, where you're going to get the same address in all cases, but in the case of B1, it's very wrong. And you could really damage yourself if you try to use it that way. Okay, so you have to use the right tool when you're lying to make your intent clear. Fair, my friends? Cool. You also have these. Let's be quick because I know time is flying. I'm going to get scolded soon. I would use them as little as I can, but there are still reasons to use them. So these are I left the link to CP reference. I think it's better explained there. They're there to tell the compiler that you know what you're doing, really. So in the n equals int of f, you're trying to say, well, I know it's a float. There might be a warning. Shut up, I know what I'm doing. Casting from a derived to an unambiguous base with casting from a D to a B, find 2 is going to work. So it's almost magical. What's there not to like? It's simple. Everyone knows about this. But the problem is that you don't know what you're doing, really. We have a complex type system. So are you trying to do a safe conversion? Are you trying to navigate a class hierarchy? Are you trying to play with const? Are you trying to play with unrelated types? What are you doing when you're doing this? So it's hard to understand your intent. It's harder for a compiler to do a good job with this, really. So what it's actually doing, this is interesting, really. First, it tries to do a const cast. Then it tries to do a static cast, but be careful, the CCast doesn't have to respect access qualifiers. So you can cast from a derived class to a private base, is going to work. So you're circumventing the type system. And then it tries to do a static cast followed by a const cast, and then a reinterpret cast, and then a reinterpret cast followed by a const cast. Oh, this is the rules. The first one that works is the one that's being used, even if the results are wrong. Yeah. This is what you get for them being clear. You can also do casts between complete types. You're on your own if you do that. One interesting case is casting to void. So sometimes you want to cast something to void to tell the compiler, well, just don't care about the type of this one. In this specific case, it's interesting because that was shown to me by library writers. Some people could be overloading the comma operator to try to hijack your system. So if you're casting one of the arguments to the comma operator to void, they won't be able to do that. So it's an easy way to avoid being hacked by malicious code. Why not? This is probably a very good use of casting to void. Casting to void is also usable to tell the compiler that you use the variable, you just cast it to void, and it's like you used it. So these days we would probably use maybe unused the attribute instead. You can also use the function syntax for this. So casting with T of an expression or T of arguments, that works. There are rules for this. You might not like some of the lines in there, but these work. The first one is not really a function called syntax, but the other one, still int of 3, auto of 3.0 is going to give you a double. Yeah, it will. And the last one is a narrowing cast from double to int. I would really recommend that you don't use that syntax for such things, even though it works, because, again, your intent. What was it? What were you trying to do there? Okay. So it's not always easy to see what you're trying to do. If you're trying to check and remove these casts because you're trying to clean up your code, they're hard to find because they look like function calls. So if you can avoid these lies, please do so. But sometimes in some niches, why not? Okay. Quickly, because time flies, we have recent casts, more recent ones. They're mostly in the library. You have duration cast. You can lie about and that's actually very useful. You read from a clock, then you have timing information, and you want them to be expressed in microseconds. You're doing a conversion like this. It's a very, very white lie. Bitcast is an interesting one. You can convert, just consider the bits otherwise, but between two objects of the same size and alignment. Very circumscribed cast there. Any cast where you store things in any object and you want to find them back in a safe way. And we have smart pointer casts because there are some things that you can do with static, reinterpret, dynamic cast, and so on and so forth through smart pointers that could put you in trouble that have been better done with the standard library function. These, apart from bitcast, they're all standard library functions that you can look at. So I left a few examples. I'm going to let you read them if you're interested. Of course, you can write to me if you find stuff that interests you, because time flies and we have to close this soon. So you have a few examples there where I'm doing a cast to seconds of this thing. Totally fine, context expert friendly, nice. I'm doing timing. I read the time it took to call function f, but I want to express this as microseconds. I don't know what the clock's duration type was. As I said, bitcast is to cast between two things of the same size. So it replaces some dirty tricks with unions and mem copies and even reinterpret casts. If you're doing this kind of low-level thing, you want to cast from, say, an unsigned integer, from a float to an unsigned integer of the same size to check the bits check the bits, you need an unsigned int. Let's pass a few slides because they're descriptions. Things like this. Well, if you want to inspect the bits and see how many bits are set, you need an unsigned int to do that, not a float. And bitcast is your friend for this. Cool. It's a very nice tool. It's context friendly, very efficient. Anycast, very quickly, it's a safe way to retrieve what you put in an any because any does type erasure. It's kind of like a void pointer. So you can store stuff there and forget it exists. But if you want to get it back, it's more complicated. So I have a few examples of implementations if you want to look at them. But if you have something like this, so you start an int, then a string, then you're trying to get back an int. It's not an int that you put in there, it's a string. You're going to get an exception. But if you do try to get a string, it's going to work, and it's fine. So sometimes casts add safety to your code. That's kind of cool, because this removes the need for some void pointer cases. And these, you can look at them, but the point is, I only gave you an example of one of these, that if you write the code yourself, you could write something. This is what it will do. But if you were trying to do it yourselves, like below, you might end up with a double deletion. I left the actual quote from the standard. So if you want to do casts through shared pointers, use the functions that do them well. So these are casts, lies, that do the right thing because users would probably do the wrong thing. So they're good lies. They're nice lies. Okay? Very quickly, short examples that I left for you. You can write your own casts. In fact, you can write functions that have the cast syntax. Like narrowcast. This one I sold from Bjarne, really. So you want to know if you would lose information doing a cast from some other type. But that's a value-based thing. If you cast an int to a short, maybe you lose something, maybe you won't. It depends on the value. There's an extra parenthesis that I need to remove there. So an easy way to do that is, well, you cast from the source to the destination. And then if you cast it back and you get the same value, you didn't lose anything. It's a simple trick. We discussed about standardizing this. We didn't end up doing it, but you can put that in your code. So you cast from source to destination. If you cast it back and get the same thing, it's a non-narrowing conversion. So cool. And you can use that in your code to validate stuff. So this looks like an actual cast, because it is. In practice, it's a function you can write yourselves. But you handle cases of types of conversions that are not covered by the standard. That's totally fine. You have nice syntax, it's homogeneous, helps you write better code. I left one last one there. This is not the Boost lexical cast. I won't check the code with you all, just pointing out the idea. Okay, for a few seconds, we're almost done. If you want to convert for something to a string, we have this very nice homogeneous syntax with toString. toString of an int gives you a string. toString of a float gives you a string. Awesome. You do the reverse? Well, you can, but you need to call a different function for each destination type because we cannot deduce the type you're going towards from the signature. So this is annoying when you're writing generic code because you have like case-by-case things to do. It's not fun. If we had a generic and general notation like this, that says when I cast to a string, I do something. When I cast to a double, I do something else. If it was handled efficiently by the implementation based on the source, which we deduced, and the destination type that we are informed of by the caller, well, we would have an homogeneous syntax that works very well in generic settings. And I left actual working implementation there if you want to look at it. Okay? With optimizations there. So to close things together, because this is all about lies, why? Why do we do that? Well, there's many reasons. There's casts in almost every language, to be honest. Maybe all of them, but at least a lot of them. And we try not to lie, but we do. And why do we do that? Well, sometimes we're maintaining old code, and we just have to patch things. Sometimes we're interacting with things that has been written by people coming from other languages. They're not correct or things like that. Sometimes we think we're more efficient, and sometimes we're making a mistake. But it's something we can check. So maybe sometimes we have things we're not proud of, design errors that we're fixing because we have code to ship. Sometimes we have a design that controls things, and we know the lies are useful and calibrated. And sometimes you just know stuff that compiler doesn't know, which is okay. So you have to ship code, you have to be pragmatic. There's other ways to lie. You could use a bag of bits and say, well, this is a T. And the compiler will say, okay, fine. You could hide code in assembly code in your functions if you think that's worthwhile. You can go through a void star to forget things about the type system. You can try to express data invariant stuff, so things that whose execution time is independent of the data you pass to them. You sometimes have to lie to avoid the compiler getting in the way with the optimization things because you need timings that are precise. Anytime you're trying to prevent time system from doing its job, you're lying really. So it's part of your life, but you want to keep it under control, of course. And you know that you have to sometimes. So if you have to do, well, make it visible. Okay, you want to be able to find the lies because you want to maintain your code and clean up stuff. Shipping is one thing, but at some point you need to clean stuff, otherwise you incur technical debt. Uh, you want the intent to be clear. You want people to know why you're doing something. And you want to make your own job easier if you want someday to remove the lies. So if you're clear from the onset, it's going to help you later. I thank you. I thank you for spending that time with me. I know I went a bit over the time I was allocated, but I really appreciate that you've watched this, and I hope that you will, well, tell me what you think.
Thank you.
Thank you, my
Thank
friend.
you, Patrice. That was really very interesting and very detailed. And we're on the online track, so we have the luxury to go over time if it's worth it. So, and yeah, so if you have any questions, I guess you already have them answered in the chat and then put them in a comment when we put it later online. Thank you, Patrice, for your time.
Absolutely. Thank you, my friend. Have a very nice day.
You too.